Testing. 1, 2, 1, 2, testing. Just testing, does the music work on this thing? Can you hear my face? Yeah, wait to sit down. Nice, everyone's ready from the toilet. Good to go. Right, okay, we're going to start. Yes, hello and welcome to the September edition of the DigitalOcean Amsterdam meetup here at Your Majesty Amsterdam, as always. My name is David. I'm the guy who sends out all the emails. I didn't send so many this month, actually. But yes, I'm your host tonight. Hopefully you managed to find somewhere to perch yourself. It looks like everyone did. Yeah, so I'll go through all the formalities and then we'll go through the presentations. Toilets are just behind you. If you smoke and vape, yeah, please take it outside. Just by the front door is fine. Don't forget to shut the door after you when you leave, because it doesn't shut because the door is broken, which is great. There is a table of stickers over in the corner there. We moved the tables around. They used to be here, but somebody said that it might be a good idea to move them, so we got more space so people can like shuffle around, which is cool. Yeah, there's lots of stickers over there, so hopefully yeah, grab a couple. There's a few stickers from like other speakers that we had last month, but it's all good. Yes, these are the people that helped make it possible. I gave Sharon a night off this month, so this month I've actually got Valerie in So you should have seen her on the way in. Yeah, and she gave you a sticker, which has been great. Yeah, so that's great. And she also is our head of gluten-free, because we need one of those. And you can go to her and demand all your alternative food choices, which is good. And as always, Hugo is running the live stream down here, and this is a particularly ravaging photo of him. Hugo and I were floating around all evening, so if you have any questions or demands, you can talk to us, and that's fine. And then thank you for all turning up. The weather is actually quite nice, so I'm surprised, yeah, that not more people turned up, but I'm super grateful. You made it through the storm. So yeah, the agenda for tonight, if in case you forgot to read the meetup page, yeah, doors open. This is the introduction. Piet is going to do the first talk from Luminis on HTTP2. Then there's a brief break where you can grab a beer, go to the toilet, chat for a bit. It's like 5-10 minutes. Then Sahil from Booking.com will give us a talk on how they use containers and deep learning at Booking.com. So that should be good. Pizzas are ordered for like 8:30. We ordered gluten-free ones because Valerie's gluten-free. She will be protecting those with her life. So if you want one, you have to be nice to her, and she might give you a slice. There's only two pizzas for gluten-frees. And then yeah, there's a lot more pizzas for the rest of us. They hopefully will turn up around 8:30, but they might be a bit later. So we shall see. Yeah, so that's good. Next one, we have the obligatory emergency slide. If there is a fire, which hopefully there's not, you have to go down the fire escapes. There's one behind you. You have to climb over like a plant pot to get out, but it should be alright. Failing that, you can go down the stairs and you go over to the bridge, and then you just stand around. It's not raining, so that's a bonus. Yeah, and we'll sort the rest out. If you hurt yourself by, I don't know, falling over a server or a plant pot, we can patch you up with plasters and paracetamol, and if it's more serious, we can do ambulance things, but hopefully you won't need that either, so that would be good. Yeah, so we've got everything covered, or we think we have. So far it's been okay. We also have a code of conduct. This lets everyone know where they stand and what to do. The protocols are in place if there is an incident. We haven't yet had to use it, but it's there just in case. I'm not going to read it all, but I'll just read the first bit. So it says, DigitalOcean is dedicated to providing a harassment-free event experience for everyone, regardless of gender, gender identity, and expression, age, sexual orientation, disability, physical appearance, body size, race, ethnicity, religion, or lack thereof, or technology choices. Everyone laughs at that bit. So basically, yeah, just treat each other nicely, and I think it should be fine. Yeah, there is a full version on the meetup group, so by being here you are adhering to that. If you don't want to adhere to it, you have to leave, but I've only had one person ever leave, but I don't think it was because of this, but it's, yeah, we should be right. If there is an incident, you can find myself, there's Hugo, Valerie at the back. You can send us a tweet. Don't send us Snapchats because I don't have Snapchat, so it just disappears. You can also take it further if it's about me. You can talk to Samantha. She runs the DigitalOcean meetups globally, and all the details are on a few slides down. So yeah, hopefully you won't need it, but it's there if you want it. Yeah, we have kind of sponsors. Your Majesty, which is on the left, provided the venue. DigitalOcean pays for all the beers, pizzas, wines, marshmallows, chairs, all the things. In case you didn't know what DigitalOcean is, they are the first cloud hosting provider to use solid state drives everywhere. You can create a droplet in 55 seconds, and everything's really simple. Like not too many buttons, and that is great. Yeah, so it's super simple. So you spend less time trying to figure out what the server does and like throwing your monitors around, and more time doing this. So that's what we all do. And then yeah, this is Your Majesty. We do design technology stuff. We're a firm because you can have partners. We have a fancy logo, and yeah, nice funky text. What do we do? This is for like NMD, which is shoes, and we put massive cubes all over cities in Europe, and that went quite well. We've also done 3D Horsey games, which won a few awards in like WebGL, so that's kind of fun. And we do lots of things for Samsung Smart Things. So this is their like TV ad stuff. So if you buy like a new TV from those guys, you'll see our stuff on it, which is pretty cool. Yeah, and this is the website. This is us. This is what we actually look like. We've got like a few more faces. This is from like midsummer a few weeks ago. It was sunny, and yeah, most of them are like Swedish, but there are girls in there, so that is great. Yeah, so the calendar. We didn't have one last month because the speaker pulled out, but I've slotted him back in November. So next month we're gonna have 2 to make up for it. We're gonna have it's like ADE week, so I tried desperately to get like on the ADE playlist playground thing. Didn't get on, but we're gonna have it anyway. Yeah, got Hort Technique gonna come and hopefully talk about those guys do Armin van Buren's light show, which is responsive because he uses the little bracelet, so that'll be kind of interesting. And then Navi, who are like friends of YM, they do lots of stuff with Unreal Engine, so that should be kind of interesting. Lots of visual stuff. Then the next week, straight after that, we're back to the normal regime. We got Edward in talking about GDPR, which is a big thing. You'll hear about it all over the place. Bart is going to talk about hunting down criminal call centers in India, which I saw at Shah, and that was hilarious. So hopefully you guys will enjoy it too. Phil Zimmerman, I'm trying to get hold of to do November. He does lots of like security and privacy stuff. He's a big name. He invented PGP, which you guys should be using hopefully. And Hank, who is the guy cancelled. He works at AMS Internet Exchange, hopefully telling us how the internet works, because on like a deep level. So that'll be good. We actually have a second slide for calendar, because in December, date's a bit up in the air, but we've got like Mandy maybe from Chef. We're doing a vaguely testy kind of theme. And then Baz Peters from GitHub, again vaguely testing GitHub related. We're doing like an end of year special, so I'm thinking of maybe doing like a raffle or something like that. I need to build on this, but I've got a few weeks to sort that out. And then yeah, in other exciting news, the meetup recently passed like 1,000 members, or sharks. Apparently a group of sharks is called a frenzy. Yeah, as I said, we had feedback from like last month or last July saying that they wanted to like switch around the layout because yeah, as I say, it used to be here and it took up a lot of space, so we did. If you've got any opinions on like the new layout or anything here, you can yeah, put it on the meetup wall, tweet, Instagram, again no Snapchat, and yeah, I will try and sort it out. So yeah, it's pretty open. Last slide. This is me with like a bush on my head from the Swedish midsummer thing, and that's Samantha if you want to talk to her. Her email is samantha@digitalocean.com, and if you want a hashtag on any of the platforms, it's DO Meetup. And that is more or less it. So does anyone have any questions? No, looks pretty promising. Okay, cool. I'll hand the floor over to you. And yeah, get going. There you go. You okay for power juice?
Well, I'm okay.
Okay.
Thanks.
That one.
Right.
I'll get to that one. There we go. Push. Does it work? Can't work. Hang on. It's thinking. No, it's projecting. Oh, there it is. Ooh.
Oh wait, I touched the wire.
Wait for a second. It's thinking, it's doing. Come on, it worked earlier. It's now like blue.
Hmm.
And then pretending to do this.
Show with the dongle and stuff?
Yeah, sure.
Is it an HDMI dongle?
Yeah, there we go. In there. It's a weird one. Sometimes it pretends it wants to be an old school TV. And does that. Oh, there we go. Right.
Okay, I won't touch anything.
Okay.
No, it wants to be that.
It goes in intervals.
Yeah.
Okay.
Alternatively, we put it on my computer. We do it like that. Is it on a stick or a Google?
No.
No.
Alright, let me just see if we can do this.
Yeah, because we can.
Does that keep it on?
No, no. Splitter? Take it out of the splitter?
It is out of the splitter.
Oh, really? Why does this do it? This is so weird.
This is
Does it repeat? What if I do this one?
Turn the projector on and off again? That's the next thing.
At least this is not live, so.
The whole of the internet to see. We're now searching. Not getting anything. Composite one. No.
didn't work out?
No. It worked so well half an hour ago.
Difficulties.
We need a slide for this. Come on.
Intermission mascot or something.
Yeah, go on.
Now it does something.
Yeah?
No?
Progress,
No, I have
progress,
the
we're
same-
doing. Hang
I
on,
have
stop.
The same problem here.
It's green.
Yeah, it still goes to flashy.
Is it my laptop that's causing this?
I feel it's the projector.
Could be.
Usually it's the projector is the source
Let me
of
just try.
Other option, can you email, post it to me? I could do it on my one.
We have Keynote, but I also have a live
Yes.
coding demo, so
Ah.
that's problematic.
That is problematic. No, we lose it. Is it worth unplugging that? But the projector is usually the pain point
Do you
here.
have Keynote
Yeah.
installed? Then I'll email, I won't do the live coding thing. Do you have AirDrop? Because it's 400
Hang on.
megabytes.
Yeah, that's fine. We can have drop it.
I'm not sure what's happening, but I'm gonna try
Okay.
Ik zei al, ik zat te denken,
Ja, go ahead.
en ze gaan naar mijn laptop en ik en ze gaan weer door.
get the flash. Interesting, because I'm only getting it
Nee,
from.
maar dat
I don't know why it does this. It's super annoying.
Well, this is a new one. Though.
Yeah, it's done this before.
Not this one.
What, the flashing? The buzzing?
We've had issues before, but not this. It keeps flushing.
Ja, maar al is ik durf. Ik waren een hele mail opgestuurd. Had hem gewoon letterlijk 300 euro in zijn hand.
Let's see, is this working?
Yes.
Yeah, it seems to.
No.
No?
Why do we get that?
Yeah, I've never seen that.
I'll send you the PDF variant too. I can work with that.
Okay. I got the PDF.
Can you start full screen or something?
Yeah. Cool. Right.
So-
We're gonna start again. We made it past our technical difficulties. Yeah. So yeah, a warm welcome for Piet.
Thanks. So that's HTTP2. Any questions? No. I promised my children I'd say good night to them first because they're watching, if they're still watching. Wat rusten. Tot straks. Okay. So that's that. I'm going to do a presentation on HTTP2, or however you pronounce it. My name is Piet. My favorite slide about me. I'm a software engineer at Luminis. I'm apparently multi-privileged. I discovered this month. So I'm white, rich, handsome, tall, and which puts me in a certain position. So if I am being sexist or racist during this talk, I'd love to hear it, not on Twitter. I'm 33 years old, but according to my kids, I have one foot in the grave. I'm almost dead, and I'm working on something called, or at least I'm trying to create a buzzword combination, product thinking. I've tweeted about it, there's my Twitter handle, and the last time I did this presentation I said I should start running again, which I did. So last weekend, this is the result. So not a great success yet, but this is an awful picture. I had a good time. So so what are we going to do? You are going to do something with your mobile phone while I talk through the history of HTTP2. Then we're going to dive into the theory of it, see how it works in practice. I had a live coding demo prepared, but my laptop wasn't going to work with me today. So it's on GitHub, so we can do it later. And then we'll do some question rounds. And eat pizza. Oh no, first your presentation, of course. Then HTTP in perspective. I think it's important to understand why HTTP2 was invented. You have to look back into where it originated from. So we have to go back a few years. So I'm going to tell about the historical perspective on HTTP. Then I'm going to talk about the actual technology of the new protocol, or the old protocol first and the new protocol. Then explain why this protocol was created, why we needed an update, and I'm going to talk about the new features in certain depth. So, a bit of history. Where do you think we'll start on HTTP? Which year? 75? No. No, 41. So, what happened in 1941? Some smart author wrote The Garden of Forking Paths in a language I don't speak. And it was it was about something what later inspired hypertext fiction. So a book where you could jump into another page in the book and then backwards create your own story, something like that. Not exactly, but something like that. And then a few years later, by the way, on the background there's some historical events you might recognize. So in this year, Vannevar Bush wrote an essay, As We May Think. It's an essay that features something called a memex, and the idea was to create a device that would create a technology or an information explosion instead of an actual explosion. So he thought we were using technology in the wrong way. He tried to do something good with what we came up with. So knowledge explosion, that's his vision. Then many years later, Douglas Engelbart created the online system. And he did, 6 years later, was finished. He did the mother of all demos. Have you ever heard about the mother of all demos? So he demonstrated a computer with a graphical interface, a mouse, and an internet connection, or at least a connection going, transferring information to another computer, which was kind of super cool at that time. It still is, by the way, especially if it works. And at the same time, these guys created something similar, or at least something to do with hypertext and hypermedia, which you will recognize from the modern internet. And they created something called a hypertext editing system and a file retrieval and editing system. So not too good on the marketing department, but still great technology. In '78, the DARPA funded the Aspen movie map, which is kind of, if you can look it up on YouTube, it looks like some sort of primitive Google Street View, where you have limited control over which direction you're going, and you can explore the town of Aspen, and you can click on stuff, or at least I don't know what clicking was called back then, but you could come up with some information screens and stuff. So that was the first hypermedia system, as we would say. Then in 1980, Tim Berners-Lee, he wasn't a SERP back then, he created Enquire, which is, some people would say that was the first website, but it's more like a modern wiki where you could edit articles and put in information. In the same year, Peter J. Brown created another hypertext system, an actual working one. So the technology was ready for an actual hypertext system in 1980. And some monk, or at least someone in the Vatican, created the Index Thomisticus, which was some sort of interactive encyclopedia. 3 years later, the interactive, these names are awful, but at least they explain what they do. So the first electronic book was published, and 4 years later, Apple Computer came up with HyperCard, which is some sort of information system, interactive information system. There was a hypertext fiction software where you could write your own hypertext fiction books. So almost 42 years later, an actual hypertext fiction software was invented, which was cool. Then in 1989, something with a wall, and the first edition of the invention of the World Wide Web at CERN in Switzerland and Italy. The idea was to connect computers so you could have information that wasn't on your computer but on someone else's computer. You could still see it without actually going to that computer. The network was invented, the actual connectivity of computers, and a browser to browse the files on another computer, which is the internet in a primitive form. Then in 1991, the first version of the HTTP protocol was written down, not in a very official manner, but still. The TCP/IP connection was created, or at least standardized, and you could do GET requests to a computer, and that's it. That was the internet then. There was no host port or a protocol name. You could just do GET and then a computer address, and then you got information. And the response was a stream of characters, because it was just text back then. And after you were done getting, the connection would be closed to the computer. So not like Twitter yet or Facebook, but getting there. Then a few years later, an actual browser was invented. Well, we would call this the birth of the internet, because by then there were like web servers that you could connect to with your computer with a browser software on it. It wasn't for everyone, but since everyone in the whole world could connect to those servers, we would call it the internet, because it was deployed worldwide. A year later, the W3C was founded, because by then the amount of web servers had exploded, so they needed some kind of standardized standards committee, and they did their work. A year later, they defined the first official version of HTTP, version 1. It wasn't a formal specification, but it was. It had headers, it had status codes, and it had a new options method, which you might know about or not. Then a year later, now the technology goes very fast. There was a pre-standard version of the HTTP standard we still use today, 1.1. And then there were all these browsers you might or might not know. I have one foot in the grave, so I remember all of them, except for links, I think. And by March that year, already 40% of the browsers complied to this standard, and a few months later, 65%. So that's quite fast, even for today's standards, or especially. Then in 1997, there was an official RFC for HTTP 1.1. We had a new required header for host, and then connections weren't closed after getting something from another server, so you could have multiple requests over the same open connection. Lots of improvements, and this is where it gets weird, except, well, SpongeBob is weird, but now the standard is kind of frozen. There are some improvements, but this is actually the standard we still use today to use, or the web browsers use to do your interneting. See, so there's an 8-year gap. where people, smart people, worked 8 years to create the same standard, but then cleared up or something. I don't know. I don't know what they did in 8 years, but Google said now it's enough. 5 years later, we're gonna do better. We need a new sort of protocol, at least an update to it, because we don't use the internet in the way it was originally invented. We don't have text pages with images and videos. We do all kind of modern stuff. So they developed Speedy, and that's the basis for HTTP2, which was standardized 2 years ago. And this is Pluto. So that was the history. If you have any questions, by the way, you can ask them now or later. Then, technology-wise, everyone know this network stack from school? So HTTP is somewhere in the application layer. The rest is just transport, linking, internet. So some terminology. So HTTP stands for Hypertext Transfer Protocol, because that's what it was originally invented for, to transfer text. And hypertext is just text with nodes in it, linked nodes. So you can hyperlink to another page. So that's a link, what we call a link. Then it's also a protocol, to confuse you, to transfer the text to clients. To do that, they had to invent a protocol suite over IP, TCP over IP, and it's in the top layer, as you can see here. So, what does it look like from our perspective? So you have a client, which is probably your browser or curl or something like that, and the client can do a request. So a request for information from another computer with a method which you might or might not know. The most used is probably get, to get the information you want. You can also put information somewhere, post it, you can delete it. If you ever build an API, you know these methods. Then the server answers with a status code, so you can determine whether your request was successful or not. Something happened. And then we have a resource. So the thing you are requesting has an address, which has these parts where you can get the information or post it. So a request kind of looks like this, and still does in HTTP 2. It's in HTTP 1.1. It's an actual ASCII text request. So you put in these lines of text, you send them to an address, and you get an answer. So in this case, you requested a web page, and you get a web page, and that's it. Your browser has to build something out of what he got back. So it's a very basic but very solid protocol. Works great, but it needs some updates. Hence HTTP 2. So what's the reason to create a new version of the protocol? First of all, as you can see in these unreadable graphs, but you have to take it from me that the web pages you are requesting are getting larger every day. So one request, it just isn't enough. Even to load a medium.com blog, you have to do 5,000, 2,000 requests. No, that's a bit much, but a lot of requests, and they have the response is of a big size, and you have to do so it's very inefficient now using HTTP 1.1. You cannot do parallel requesting and responses, not really. You could, but there's a chance of congestion. If you request two resources and the second one is fast but the first one was slow, you have to wait for the first one to arrive before you can get the second one. So you can have network congestion, which is awful. There's a lot of overhead. All these headers get sent over the line every time you do a request, even though they are fairly much the same every time. And if you want to get a fast website, you do have to do a lot of hacking. As you might know, you can create image sprites to prevent doing 20 requests for 20 images. You can do some data inline, domain sharding. All cool technologies, but they're hacks. And HTTP 2 will solve some of these problems. So how is it going to solve it? First of all, it's not a plain text protocol anymore. So if you do a request with HTTP 2, it's a binary request. You get a binary response, which kind of sucks because it's harder to teach HTTP 2 to people than but you can parse it, but have your computer parse the request so it looks like a human request. There's something called multiplexing in HTTP2, which is super cool, and it basically means that you can get your data in parts, and the client has to solve the parts of the puzzle and create the response itself. So you don't have to send it in one go, basically. You only use one connection, so if you ever looked at a browser request, requesting a browser, you can see that you mostly do 5 simultaneous requests to a server, and that can cause network congestion. So HTTP2 standard says just one connection per session between a client and a server. That's kind of cool. It's more fair on the network as well. The headers are compressed now, so if you do a lot of requests with the same host name header, then you can just do a compression algorithm and get less data over the line. And there's something called server push, which is super cool. I will I can't demonstrate that. Can I curse? No. And it's compatible with HTTP 1.1, so you don't have to update everything to be able to use the new protocol. You don't have to update your whole software stack. So what are these new features? First of all, the binary protocol. So HTTP2 lives somewhere here. So instead of packets sent over the line, you have now a binary protocol that is more compact on the wire. I'll explain it later, but it's harder to read, as I explained before. Where is this? Right. So instead of a request and a response where you get a whole response object, as it was in HTTP 1.1, you now have streams, messages and frames. So a stream is just a bidirectional flow of bytes that go over the same connection back and forth. A stream contains messages. One message is just a sequence of frames. They don't have to arrive in order, but that's what they are called together. So the smallest unit of a message is a frame. So these are frames, and together they form a message that gets transported over the stream. So that's how the protocol works. Then multiplexing. This is not very hard to understand if you use an image, but I thought, what if we can demonstrate it here live to see what the advantages of multiplexing are over the usual HTTP 1.1 slow protocol. So we are going to play request response. It's a super fun game. So I'm going to be the client today, and you are going to be the server, and some of you are going to be resources. So I request a application.js file, and someone is going to respond with the resource. You're going to respond with the application.js. Could you respond with an image? And then there's the index file. That's for you. All the way back. So this is how a server actually works. Not actually, but from a human point of view. So I'm gonna play client now. Okay, so I'm gonna do a HTTP 1.1 request for 3 things, namely an index file, an image, and a JavaScript file. So I usually do that in that order. I have to have the index file first because I don't know what's in it. So can I request the index resource, please? So now, yeah, you have to bring it to me because we're playing client server. So there's the resource. It's really slow. Thank you very much. Thanks. So,
yeah, you get that with service. Yeah.
So as you can see, the image and the application are much faster to get, but I have to wait for the first request to respond, and then I can parse it. Oh, look, it's an index file. It has an image in it. Can I request the image, please? Then I get the image response. Thank you very much. And then an application file. That was very fast. Thanks. Oh, no. Not again. Do you have a password?
Yeah, keep up.
No one's watching anymore anyway. So, multiplexing is different because you don't get a response, you don't have to wait for it, and you don't have to wait for the whole response to be returned before you can get the rest of the stream. So we're also going to do a multiplexing demo. I have some stuff prepared for that. It went a little wrong last time, so I have some precautions. So otherwise it would be quite expensive to do again.
Oh my god, that is your
I'm
kitchen.
going to protect my clothing. So there's a nice carpet here. You can't see that on the live stream, but I promised Dave to not make his carpet filthy. Some protection from me, something to bite on for the screams. So, who wants to volunteer for a multiplexing?
I think,
Sorry?
yeah, sorry, there's a no saw policy.
No saw policy.
So I'm gonna take that. So.
Oh, okay. Well, that's a shame. Oh, was it in the code of conduct? It's no saw. No.
Next month we'll have saws.
Okay. Well, how am I going to explain this then? Well, you have to take it from me. So if I would request a index file, I can get it back in pieces. So you have to imagine a resource being cut up into pieces, screaming, blood everywhere, and then I can puzzle it back together. I'm not a doctor, but I think I could have done it. Anyway, and then there's the coolest feature in my opinion, which is server push. So I had an index file which I requested, and if you would have a smart server, it would know that if I would request the index file, I would also need a JavaScript file later on, or immediately, some style sheet, for example, and an image. And with HTTP2 you can do just that. So if I request an index file, the server can respond with the index file somewhere here, cut up into pieces with blood, and it can also do a server push of a promise of another file and another file I will need for this to with this request. So a smart server can figure that out and push multiple responses for one request, which is kind of cool because in most use cases, for example, for a web page, you would need more resources than one, and the server can push them to you. I had a live demo of that. You can look it up on my GitHub. I have the link somewhere. But what happens is you can see that in the browser. So I request the index file. It responds with an HTTP2 response of the index file and 2 or 3 push promises, and then you can see Chrome trying to have the server deliver on the promise. And what I thought would happen when I didn't read into this yet, that I would immediately get all resources, but at least in the case of Google Chrome, it waits. It parses the index file first, and the index file sees if it needs a CSS file or an image, and then tries to signal to the server that it needs the other files as well. So it's not super fast in the case of a web browser, but if you're, for example, if you are making the client yourself in case of some microservice that is connected to another microservice, if the protocol between those is HTTP2, then you can, and you trust each other, then you can immediately ask for the push promise to be delivered. So it can be fast, but it's not always as fast as you would think it would be. Like me last Saturday during the run competition, but a good time nonetheless. Anyway, another cool feature is header compression. So if you're doing 5 or 100 requests that all have the same host name, the same method, the same scheme, the same accept header, the same user agent, then why would you send that header or those headers every time you do a request for the same session? So the simple answer is you wouldn't. So what they came up with in HTTP2 is some kind of compression algorithm. It's called, well, Huffman encoding already exists, but it's called HPEG. It uses Huffman encoding to reduce the size of the headers you are sending over the line. And how it does that is a bit beyond the scope of the talk, but from a bird's eye point of view, the first request is parsed, also very efficiently, because you don't have to write out method every time. You can just come up with an ID for method that all browsers would know. And then for all subsequent requests, only the diff of the two requests is sent. So we already did all these headers. Now the only thing that's changed for the second request is a path. So the next request only contains a path, the diff of the two headers. So that would reduce the size of your headers. I don't know where I came up with this number. I heard that what... Oh, sorry, you have a question.
What happens when you use multiple HTTP2 servers? Because one might know the question you answered asked before, but the second now might not know.
Yeah, exactly. So the question is, what if you have two servers that you're going to do requests on? So in that case, they both have an in-memory set somewhere of the request headers it received, but if they're not connected, they're going to do their diffing on only the request they received. So it's less optimal then. But still, there's compression for the second request. It's backwards compatible, at least it tries to be, and clients and servers try to be friendly in terms of negotiating the protocol. So if you do a request to a server that supports HTTP2, the client tries to negotiate over the response and the subsequent responses, which protocol to use. And they have invented a protocol negotiation for this, and it's basically an extension of TLS. What it does in practice is the client requests or sends a client hello to a server. The server responds with something that the client can or cannot understand. If it can, it tries to negotiate the spec, and then it from then on it will try to do HTTP protocol. If the client doesn't understand it, it parses gibberish, it sends a request again, everything is fine. There are some more features, cool features. One of them is that by chance the protocol is inherently more safe, because no browser, at least not that I know of, does HTTP2 over a non-secure connection. So you have to create a secure connection to do HTTP2, unless of course you implement the client yourself, then you can do it over an unsecured connection. But that's a pro, I would guess. Then I saw some of you looking at this sheet weirdly. So you were thinking, what if this response is more important than this one? How will I know that I will get it in time? How can I negotiate a faster delivery of a more important resource, right? So they came up with a solution. It's called stream prioritization. So you can prioritize certain streams, and the protocol tries to deliver them faster, but I can't promise anything. And there's something called flow control to prevent congestion of your of the line. Yeah, this is not possible. It's funny, but my computer is broken. So in action, we're not going to do an action. I'm going to tell you where you can find the action online, which I usually do in these hours. So in the wild, there are some implementations. So, well, this I won't cover now. It's not very exciting. But there are already a lot of servers that support the new protocol. This sheet is already a few months old, so there are probably a lot more, and the new versions as well. But most application servers I have used support the new protocol, so you don't have to do anything basically to upgrade to HTTP2, which is cool. By the way, this is the name of the protocol, There were lots of them before. These are all working versions. But if you would open an HTTP2 connection, for example, if you would go to twitter.com on Chrome, you would see that this would be the name of the protocol for some requests. Do you have a browser that I can open here, or is it dangerous?
No.
Where's the mouse?
Oh yeah.
Yeah, so you can do more.
Then I can show it.
Yeah.
The new win. Okay.
And then you got to drag it over here.
Right. Okay.
That's it now. Yeah. Go for it.
Okay, thanks. So maybe I can demo some of the new protocol. So if I open the network, if I open David's history browsing,
This is dangerous.
this is hard. Okay, so I'm going to go to twitter.com, and look, this is hard to read. Can I open this in a big screen or something?
Yeah.
I'm not good with computers. Where is it?
On your way. Drag it to your
You
right.
can also mirror the screen otherwise.
All that.
No, this is okay. So you can see here that we requested some resources, and the Twitter servers responded and tried to use the HTTP2 protocol to get the resources back to you, which it succeeded in. And I don't see any push promises, but this is the proof is in the pudding, right? So this is almost all HTTP2 protocol between you and Twitter.
Piet, is there any way that you can indicate perhaps the speed up due to the compression that you were talking about?
No, not really. You have to believe me. That's one of those privileges I have. So I tell you, this is better, and then you believe me. Where?
And then you do 3 fingers to your left.
3 fingers?
Wow,
Whoa.
impressive.
Mike can do that too. Anyway, so a lot of clients also support HTTP2, a lot of browsers, even a certain browser with a blue E as an icon. Is it still blue? I don't know, never use it. So this is not what we're not going to do, but you can roll your own HTTP2 server. There's a link here somewhere. Here, this is a link to my GitHub page, and if you check it out and you follow the instructions, I have documented my project for once. Don't tell my boss, but if you follow the instructions, you will create a HTTP2 server on your computer that delivers an index file, a few images with a push promise that your browser tries to deliver on, which is very cool. But yeah, that's another one of those believe me privileged things. There's also a Docker container. That's the bridge to your talk. Okay, so what is the? If you still don't believe me, which I find very hard to imagine, but by now, why HTTP2 is better than 1? So this is an optimal request response scenario with a few resources. So for example, if you have a very fast, low latency network. So in HTTP 1.1, the old standard, you would do request response. Oh, another request, another response. So very slow. There is something called pipelining in HTTP 1.1 since I don't know, a lot of years, and that tries, if it, for example, if it fetches an index file and it sees, oh, I need a CSS file and a JavaScript file now, it tries to do multiple requests to a server parallelly, probably, and then the server tries to deliver them in this, as fast as possible, which is faster than it was. And with HTTP2 you have multiplexing, as I explained, which in practice can be a little faster or almost as fast as pipelining, but over one connection, not 5 parallel connections. So that's already a pro. And with push promises, if they would work as you would expect, which they don't in a browser, it would be even faster. On a high latency network, for example, on your mobile phone, or if you're in a crowded office or at an event, or driving the train, then the advantages are very visible, because high latency means the request will reach the server very late, which adds up to the response time, and before you know it, you are going to close because you don't want to wait on delivery. With multiplexing and pushing, this is much better than HTTP 1.1, which I'm going to demonstrate now. So this website tries to simulate a high latency connection over HTTP 1.1. So let's do a perfect connection first. Do we still have time? A few? Okay, so a perfect connection HTTP 1.1. You can see that all requests arrive in the order all responses arrive in the order you requested them. Then with 5 parallel, I cannot demo that, but with 5 parallel response lines. But still, it's not the fastest. In HTTP 2, you do a request, or multiple requests on the same connection, and you get all responses on the same connection multiplexed. So what if we increase latency? What if you're on a bad network on a mobile phone? Then using the old protocol, the responses, all the latency adds up to the response time. So it takes a long while for the image to complete, for the responses to complete. And with HTTP 2, you still have the latency from the request to the server and the response back. But once the requests have reached the server, the responses will follow in one stream. Because it doesn't have to wait for a subsequent request, because the connection is open anyway. So, see, so the difference is quite noticeable if there's 1 second of latency. So there's about a 1 second latency to the server and 1 second back, and then all responses stream in. And with 1.1, that's undoable, because every request response cycle has latency. Now do you believe me? 3-finger swipe. Findings, as if I have researched this. Well, I would recommend you switch over immediately, but use the protocol and negotiation thing, because if your client doesn't speak HTTP 2, they are in bad luck. It was not hard to use the protocol. Do not roll your own protocol negotiation thing. There are lots of libraries to use. This is more a note to myself. Before you assume stuff, try it out. I gave this talk one time assuming something was true and it wasn't. It's such a shame. I started with a web project because the aim of the protocol updates, or at least the people they had in mind, the applications were mostly web applications. Then it really shines. And if you're debugging your connection, don't forget a decryptor. Wireshark has a decryptor because it's all secure. So you have to decrypt the information that's going over the line. And read the documentation. Another reminder for myself. Then, if you want to read more, I can't imagine there's anything you would want to know besides this, because it was a very complete, thorough, high-quality presentation. My boss is watching the live stream. Then these are the sources you can read. There's also a good book on O'Reilly that's very in-depth. Yeah. Go to my Twitter and link me on LinkedIn. This is networking, right? This is how you do networking? Yeah. So, any questions? I knew it. No questions? Yeah.
Wait, I'll do the cricket.
One is for HTML pages, is pretty obvious because there's also CSS and JavaScript images. Are there any specific advantages you've seen in terms of APIs, like JSON and stuff?
Well, it depends. If you only do.
Repeat the question.
Oh, sorry. The question is. The question is. So there are obvious advantages for web-based, browser-based use cases. But what if you have a client and a server that only that have an API that does JSON request response? Then there's not too much of a advantage. But I saw a presentation on Google. RPC something, and they used HTTP to communicate between two. Someone is nodding. I'm right? gRPC. Thank you. They use HTTP2 as a protocol between nodes. So must have some advantages. I forgot which, but there certainly are. Yeah. Especially if you use a binary protocol instead of JSON to do the responses. For example, if you use Captain Proto or something. Super fast, and it's an open connection that you can reuse, which is also an advantage. It's just one pipeline. Did I answer your question? Little? Okay, cool. No, any more questions?
Just, as I understand, standard general purpose web servers doesn't support push, right?
Not. No, that's right. Oh, right.
And
Okay.
That's why actually you wrote this prototype to measure the speed. Right?
Exactly.
But browser does support it.
Yeah. So the question is, the usual web servers like Nginx and Apache don't support push as we would think they would support it now. It's on the what do you call something that you were gonna do but never gonna do?
To-do list.
To-do list.
Backlog.
Backlog. Exactly. So it is on the backlog, and I don't think it's in either of the web servers yet, but I think someone proposed that, for example, you could do something. If you for example, if you had an index HTML index page, you could mark resources as pushable or something, and it would be parsed by the web server, and it could be standardized. I don't know. And then the web server would know which resource to push if a request was coming in. But until then, you have to do it yourself. So you have to build in some kind of logic to do it yourself. But I can imagine in a few months or years you can do some sort of smart push configuration, or maybe even a configuration file. And any other questions? Okay, then thanks for attending. And you're up, right?
No, there's a break.
Oh, there's a break.
Yes, thank you for your presentation. It was really interesting. Thanks for being considerate about the floor, because don't want to make it messy. We're gonna have like a, let's say, 2-3 minute break. Head to the toilet, grab more beers. We'll be back straight after. I don't know Sahil's password, so yeah, I'd probably avoid doing that.
It's good that you don't know.
It's good, it's good. Yeah, so if you want to see Pete's demos, he's going to hang around during the pizza. You can come up to him and hopefully you won't have too many sticky fingers, and you can do demo things on his laptop. And failing that, we will put all of the links on the meetup page, and I'll send out emails too. And yeah, one way or another you should be able to see them. So that'll be good. So yeah, next up, deep learning using containers with Sahil. So warm welcome.
Thank you. So my name is Sahil Dua and I work at booking.com. We had a really nice presentation by Piet. Yeah, thanks. Good. So yeah, it was really entertaining, and I would try to make it entertaining as well. So I will try really hard to crack some jokes. So if you see any joke, please laugh. Thank you. It was awesome. Okay, so before I start, let me see like how much the audience already knows about the topic. Can I see the hands of people who have written application that runs in container? Quite a lot, okay. And those who have used deep learning, and those who know what deep learning is. Okay, almost all. Okay, cool. So this talk is going to be a unique combination of deep learning as well as containers, as you will see very soon. So first of all, what are we going to talk about? First of all, I will mention some of the applications of deep learning that we saw at booking.com, and then we'll proceed to talk about the life cycle of a model, a deep learning model, like what are the different phases of a model, and what do people do at different phases. Then we'll talk about the pipeline, production pipeline, which contains deep learning, containers, Kubernetes. I hope I covered all the buzzwords. Okay, so something about myself. Who am I? I'm a backend developer working on deep learning infrastructure at Booking. I'm a machine learning enthusiast, which means I spend a lot of time in learning about different techniques and different frameworks, technologies coming up in machine learning area and deep learning. And I'm an open source contributor. I've contributed a couple of patches to Git that I think most of you use. Pandas library, data analysis library, and a bunch of other projects. Kinto by Mozilla, GoGitHub by Google. And I'm a tech speaker, that's why I'm here today on this side of the podium. So let's start with the applications of deep learning at booking.com. And before I talk about it, let me talk about the scale. We have more than 1.2 million room nights booked every 24 hours in more than 1.3 million active properties across 220 countries. And this is also sort of outdated something. It's quite more now. So I'm not showing off the numbers here. That's not why I'm here. The point of showing these numbers is that we work at a huge scale, and that provides us access to a huge amount of data, and that we in turn use to improve the customer experience. So let's see what are the applications of deep learning when we have a lot of data. So the first application is image tagging. When we see this image, there is one question: what do we see in this image? Now this question is really easy as well as a really difficult one. So it depends whom you ask this. If you ask this to a person, to a human, this is a really easy question because we can see there's a chair, there's a bed, there is a TV. But if you ask this question to a computer, it's not really a very easy one. Why is it a difficult problem? Because the context matters a lot. And what I mean by that is if we pass this image to some publicly available image tagging like ImageNet or DenseNet, these are the results that we get. Oceanfront, nature, beach house, apartment. Okay, it's apartment. Okay, what do we do with that? how do we use this information at booking to improve the customer experience? We can't. So these are the things that are important for us to know about a particular image. Sea view, is there a sea view from this particular room? Is there a balcony, terrace? Is it a photo of a whole room? Is there a bed in the room? Yeah, things like that which we can use, which provide us context about what's there in an image. And while you may think that it seems like, okay, we just need to identify what the objects are there, it's much harder than that, because first of all, this is not an image classification problem, it's an image tagging one, which means there are going to be multiple tags, multiple labels for each image. This is one challenge. And another one is there is going to be a hierarchy of those labels, which means if you see a bed, we can guess that this image is going to be of the interior of a room, unless you are in such a room where there is only bed and no actual room. So, sorry?
Where is that, by the way?
I can share later. I don't remember. So once we know what's there in an image, we can use that information to help our customers, and we actually do that, to help our customers make a decision about where they want to stay based on different features that we see in the images. Another application is recommendation engine. It's a classic recommendation problem where we have a user X booked hotel Y. We have a new user now. We want to recommend hotels which that new user is going to book or is going to like more than some other random hotels. So the objective is we want to find the probability of booking a hotel for user Z or Z. We have some user features like country and language of the user. We have some contextual features like when the user is looking for a hotel, day of the week, season, and a bunch of other local factors. Then we have item features about the hotel, about the property, maybe apartment or anything, like price, location, and a bunch of other things like what are the facilities available, what's there in the neighborhood, and all that stuff. So I'm not going to go into the detail of recommendation engine problem, but the research shows, which is not done by me or people at Booking, it shows that we can get better results if we use deep learning instead of using the other collaborative filtering or other techniques that we used to have and were really considered really good for years. So once we know what are the applications of deep learning that we could benefit from at Booking.com, we started exploring, and thanks to my colleagues who might be at home at this time, Stas and Imra, who actually started exploration of deep learning at Booking, and these days we have some applications, some really nice models in production at Booking. So, life cycle of a model. What are the different phases of a model? Code, train, and deploy. What that means? So in the first phase, data scientists write their model, write the code for the model using any framework. We use TensorFlow. So they write their model, they try out with different kinds of features, different kind of embeddings, different kind of architectures, different hidden layers, and all that stuff, all the hyperparameter tuning. And then once they are happy with the performance of their model on their local machine, they want to train on production data so that they have the final model. And once they have the final training on the production data, it's time to deploy the model so that the clients can use it and we can serve the request in real time or offline applications depending on what the client wants to do. So I've been talking about the production pipeline I mentioned in the agenda as well. So these are the two steps, train and deploy, which these are two phases which are covered in that pipeline. And some of you who have experience with machine learning or deep learning already, you may wonder why training is a part of production pipeline, because sometimes you can also train the model on your laptops. But if you try to train a model on your laptop, you may end up looking like this. So there are a couple of reasons, like your laptop may not have sufficient resources, like sufficient number of cores, sufficient number of GPUs on your machine. So it's better idea to not. Is there an indication that it's? So yes. So sometimes when you don't really have enough resources on your laptop, it's a nice idea to test your model, to write a model and try out different kinds of architectures and different kind of hyperparameters. And once you're happy with it, it's a good idea to move to a heavy server where you can get a lot of resources and actually do the training on production data in actual production servers instead of your local laptops or machines. So this is what we do. We have big servers which have a lot of cores. It's not that big, but yeah, it's still big. So we have servers which have a lot of cores and a lot of GPU support. It's not visible yet, yeah. And what we do is we have our training script. We ship it to our server, run it there, and done. But there are a couple of limitations with this. There will be multiple data scientists running their training script at the same time. So we want to, if we want to provide the independent environment, we may not be able to provide that. And yes, that's how I'm going to lead to containerization. So this is what we do. We wrap our training script in a container. We run our container on one of our servers. And yeah, every training is running in an independent environment. And all that stuff that comes with containers, we get benefits of that, having all the dependencies, having different versions of TensorFlow. If one data scientist wants to use, like, let's say 1.1, or another one wants to use 1.2, they can just ship their dependency with their container along with their training, and they can run their specified version that they want to run. And they can also use the GPU. The containers can use the GPU support from the servers and speed up the process of training. So in a nutshell, this is how the training of a model looks like. We have our data, production data in Hadoop storage. Every time we want to train a model, we spawn up a new container which has all the dependencies and the training script. It takes the data from Hadoop, the production data that we want to use for training. It runs the training, and once the training is over, we want to make sure that we are able to store that model that was trained in that container. So this is what we do. We store the model checkpoints back to the Hadoop storage, and model checkpoints are basically the model weights that are learned over the time during the training, like parameters, weights. And we store them back once the training is over to the Hadoop storage, and the container dies. Yeah, who can be more selfless than a container? It takes birth to do the stuff that you want it to do and dies. You were supposed to laugh. Thank you.
So you're training against a subset of your production data? The entirety of it?
It depends. So we have different scripts which prepare the data for us. Like if if I'm a data scientist and I want to use some particular subset of our data, there's going to be a Uzi workflow or a cron job which prepares the data for us. Then we take it and we don't really do the processing of the data right at the moment of training. Fetch that and train.
Thank you.
How are GPUs assigned to your containers? Because the way you sketch it now, you still have the problem of sharing your GPU resources between multiple containers. They still are competing, I guess, for the same resource.
Yeah, so I'm going to mention that later in the slides. We use Kubernetes. You spoiled it. So we use Kubernetes, and it helps us to link the GPUs we have on our servers to the containers that we build. So it's like a container is an object, and like it's a pod. So it helps us to link the GPU to a particular pod, and once it's used by one, it can't be used or accessed by any other pod. So if we have sufficient
queue of containers that are waiting for GPUs.
Yes. If we have limited number of GPUs, we can have a queue of pods which are in a pending state, and they can run once the GPU is free. So yeah, container dies, and we have the model. What do we do next? Now we want to deploy that model. So what we did was data scientists wrote the model, tested out different things, trained in production data with production data, and now we want to ship the model, like productionize the model so that the clients can use it for getting the predictions on their data. So we have a Python app which runs in the container again. What it does is it takes the model weights from Hadoop storage, which we just stored in the previous step, and it loads the model in memory. So to load the model in memory, we need two things. We need the model definition, all the information about what are the features, what are the inputs, what are the interactions, what are the dimensions of hidden layers, and all that stuff. And then we need all the weights that are trained during model training, like all the model checkpoints. So it loads the model in memory because it has the model definition in the app, and then it loads some weights from Hadoop storage, combines them, and loads the model into the memory so that it's ready to serve the request and serve the predictions from now on. And to top that, it provides a really nice URL, nice, easy to remember URL to get predictions. So in the end, it boils down to sending one GET request, and it's HTTP 1.1. We're not there yet because browsers don't support and all that stuff. So yeah, we send GET request with all the input features that we want to predict on, and get the response back with the predictions that you expect that app to give back, depending on what model is running. So once we have this model deployed in production, the next step is we should be able to measure the performance of serving. How are we doing? How much time is it taking? What's the latency and all? Okay, before that, so let's talk more about the deployment. So this is what we have. This is what it looks like. We have the app, and it's running in the container again. And what happens, as I described, is client sends the input features and gets the prediction back. But since we have a lot of requests coming from the client, we need more containers. So we spawn up a lot of more containers, a lot more than 6 for sure. And we have a load balancer, which is responsible for distributing the request across all the containers. And client doesn't know about all this and just interacts with the load balancer IP, and yeah, apps serve the request. But since we work at a huge scale, we need a lot more containers. And as we keep increasing the number of containers, we need to have a way to manage all these containers, because if, let's say, one container dies, what do we do about it? How do we know about it that one container has died? So what we do is we use Kubernetes. That's why I said it was a spoiler. So Kubernetes is a really nice open source tool, which is a container orchestration platform. And what that means is it helps in managing, scheduling, and I forgot one verb, but yeah. So it really helps us in managing all the containers, all the cluster of containers, and there can be multiple clusters of containers as well. So for example, it helps in scaling up or down. It helps in maintaining a particular number of containers for a particular app. For example, if one of the containers dies, it's going to spawn up a new container with all the same configuration as other containers and going to put that into the pool. So it makes sure that at any point there are always a fixed number of apps, like containers. It also helps in auto scaling up and scaling down based on the various features like CPU usage, number of requests coming up, and all that stuff. So it's really handy when you want to manage a cluster of containers and want to be able to easily scale up and scale down. Okay, now we talk about performance. So if we know that our model takes some computation time to compute on all the input features and takes some time to compute the prediction, that is not going to be the time that's going to be seen by the client, because there's going to be some request overhead, and so the total prediction time is going to be request overhead plus computation time into how many instances you have in one request, because you can send like 10 or 20 instances of input features in the same request and get all the predictions back in the same request. So once you know this thing, you know that if your model is really simple, that means if it has a low number of features, a low number of hidden layers, the computation time is not going to be much, and you know that request overhead is going to be the bottleneck for your serving. So you need to be aware of what kind of model you have, so that you know about the performance and you can optimize accordingly. Like you know what you want to optimize on. Let's talk about two different aspects of that. So one is latency and another one is throughput. Let's talk about them one by one. So latency is the amount of time taken by a request from a client point of view, and there are a lot of things that you can do to optimize for latency. And so the first question is, why do you want to optimize for latency? You want to optimize for latency in those cases in which you have real-time serving to your client or customer. So what you can do is do not predict if you can pre-compute. So if you want to deliver the request really fast, do not predict real time. If you can do this, like sometimes you have limited set of features where you can already pre-compute all the values, have a lookup table, and serve the request from there. Yeah, someone said really nicely that if you want to optimize for latency, don't serve anything. So yes, don't do anything in the real time. So another thing you can do is reduce the request overhead. There are a bunch of different things that you can do. Like one of the things that we do is making sure the model that you're going to use is right there with the app, so that it doesn't have to make another request to the model. So that's why we load the model into the memory on our app server, so that it's once it gets the request, gets the input features, immediately gets the prediction and sends the response back. So there are a bunch of things like that, which you can optimize to reduce the request overhead. Another one is predict for one instance, and since we already know that the total prediction time depends on how many times you compute. So if you want to get the response back immediately, always predict for one instance, send multiple requests for all of your predictions. Then there are some specific techniques like quantization, where you lower down the resolution of your data so that you lose something on precision, but then you lose then you win a lot on the performance, on the computation speed, because now your CPU, your processor is able to handle 4 times more data, and it can compute things faster as compared to the float 32-bit value. And then there are some TensorFlow specific techniques like freezing the network and optimize for inference. What does that mean? Freezing the network means if you have some variables, you change them into constants so that it computes faster on the prediction time. And another thing is optimize for inference, which means you remove all the unnecessary nodes, or you remove all the nodes which are not being used right there in the computation from your TensorFlow computation graph, and hence you speed up the process of computation and serving the request. Another option is optimizing on throughput. Throughput means the amount of work done in unit time. Why would you want to do that? You want to optimize for throughput when you have some, let's say, cron job or Uzi workflow which has to do a lot of work, and you don't really care about how much time one request takes. All you care about is how much time it takes to complete all the work. Again, do not predict if you can pre-compute. Of course, if you don't do anything in real time, it's going to be fast. This is a really useful one, batch request. When you know that all you care about is getting the work done as soon as possible, you should batch your request, which means you send thousands of instances to predict on in the same request. And that makes sure that you gain on the request overhead, which is not going to be there for all of those requests. So you have only one request overhead, and all of that is going to be the computation time, and you get more work done in unit time. And another thing is parallelize your request. Send multiple requests at the same time without waiting for the response, and sort of do it asynchronously. This is something that we do a lot. Actually, we do both of these techniques, batch request as well as parallelizing, and it really helps in getting a lot of work done in less amount of time. Okay, we are nearing the end. Not going to take a lot of time because I know you're waiting for food. So let's talk about, let's sort of try to summarize what we talked about. First of all, we talked about the training of models in containers. What we do is spawn up a new container, get the data from Hadoop storage, run the training, store the model weights back into Hadoop storage, and the container goes away. And next, we deploy our models in an app which has model weights and model definition, loads a model, and is ready to serve the predictions over GET request, GET HTTP 1.1. And we use Kubernetes to manage all of our containers so that we can easily handle, easily scale up, scale down, and maintain a particular number of containers for a particular app. And then we talked about optimizing serving for latency and throughput. Depends on what you want to optimize for, because it depends what your client has and what you really want from your client, whether you care about a lot of work done or serving the request quickly. And if you want to follow me, you can find me using the username Sahil2305. Yep, and that's it. Thank you. Yep.
So I'm curious, in production when you're doing inference, do you still use GPUs for all the application servers, or is it all just on the CPU?
On the time of inference, you mean on the time of when we are, so the question is that do we use GPUs for prediction time as well, right? The answer is no, not at the moment, because we realized that not using the GPU on the prediction time was still within the boundaries, within the limits of our latency, so we didn't really try to use the GPU for inference.
Okay,
yeah.
thank you.
Yeah, you mentioned in your first slide you had some specs on the hits and the bookings on the site, but that's not the same as the amount of predictions that are being done. So I imagine that predictions are done in front of that. So do you have? Can you share any numbers regarding the amount of hits against the prediction engines?
No, I'm afraid. Sorry. No, sorry.
No, no worries.
Yeah.
Do you use TensorFlow serving in production, or just load the original checkpoint into memory?
So do we use TensorFlow serving? No, we don't, and we plainly do it in a way that I described, that we load the model weights, and once the model is ready to be predicting, we use that to predict our model. So we're not using TensorFlow serving at the moment, but yeah, we are moving towards that, and it looks like a nice alternative that we may utilize.
Okay.
Yeah. Yes?
So why did you have these multiple containers? My idea was that you're ending up with one model. You want to end up with one model, right?
Yep.
So why the multiple containers?
Okay, so why do we have multiple containers? It's the same problem as the distributed system problem, that we want to have more than one instances of the model of the app that is serving the predictions. So it's not so all of those apps have the same model loaded into their memory. It's just a replica of each other, and they are just there as the replicas to make sure that we can serve a large number of requests. So there is still, so the cluster that I showed was still for one. Yeah. So this cluster is still for one model, and we have multiple clusters for multiple models, and all of these apps, all of these containers have the same model loaded, and we want to make sure that we are able to serve large number of requests. That's why we have large number of containers.
It's faster?
Yeah, it is, because now it can serve more work. because we distribute it, and otherwise it's going to be limiting on how many requests it can serve. Yeah. Anyone else? Okay, food time. Thank you.
Yeah, okay, so we're just waiting on the pizzas. They should be here any minute. Yeah, there is beer and wine and Coke in the meantime, and a few snacks. And I'm going to give the pizza people a shout. And there it is.